out this video, but we'll see. Okay, first thing is Wednesday is the day before Thanksgiving. I am not allowed to cancel classes. Get in big trouble for that. So I plan on being here, all right? And I would like for you to be here, but if you don't make it, then, you know, I'm not going to penalize you for it. I'm not going to give a quiz that day, but you're responsible for what you miss. I will record the lecture. If I come and there's like 2 people, I don't think I'm going to have class. I don't know. I'll probably just give those people bonus or something for being here. But I'm just letting you know that, like, officially, we're supposed to have a class. All right? Yeah, now you're all going to be here, right? All I have to say is bonus and everyone's here. Okay, so we have a lot to do, and that's why I don't have time for quiz. What I think I'll start with is there was something I did not cover that was in your homework, but I didn't. Guys, come on, man. Y'all just sit there and chat like this is like social hour. Go in the hallway and chat. It's fine, but it's rude. I've said it like how many times this semester? Like what, 6 times? Right? Okay? If you want to chat, just go in the hallway. All right, so I did not cover the error estimation, which was part of your homework. You're asked to determine convergence or divergence. So it's really something I don't focus too much on, and the reason why is because it only works for alternating series. So, if you have an alternating series that converges, then you can use this theorem. But I'm just going to run through it real quick. It's in the book. It's called the alternating series. Alternating series estimation theorem. Okay, so if we have an alternating series, this really doesn't matter if it starts out a positive or negative. Okay, if we have an alternating series and it passes the alternating series test, and that means that it is a decreasing or descending sequence, right? And that the limit of the sequence goes to 0. So if you just go back, look up to your cheat sheet. If we pass the alternating series test, then it converges, right? And then what we have is this. Then we have that the absolute value of this thing called R sub n, which is basically the error, okay? This is the error, is equal to, just let me write it first and then I'll explain it. All right, so what this is saying is that when we have an infinite series, right, it goes on forever. So you can never really add it up because you have to add forever. So if we ever stop anywhere in the series, then that's going to be an estimate, right, if we make it a finite series. And the amount of error that we would have if we stop somewhere from the true sum can be calculated. So this right here is the true sum. This is the estimate because it's a finite sum. So you remember S sub n meant the nth partial sum. It meant that you summed but you stopped somewhere. So if we take a look at the difference between the true sum and the estimated sum, okay, where we actually stop the addition of things, then that error must be less than or equal to a sub n plus 1. Okay, so all this is saying is this. I mean, this is the note, the way it appears in the book. When we look at this sum, right, when we look at that, that's actually something like, depending on where it starts, a sub 0, then minus a sub 1 plus a sub 2 minus a sub 3. It might start negative, but that doesn't really matter, right? So we have this like, something minus something plus something minus something. If we go and we add this up forever, we get this number. But if we stop, let's say we stop, I'm going to run out of room here. Let's say we stop at a sub n, right? Then that would be the nth partial sum if we stop there. Agreed? If we want to know how much this sum differs from the true answer, then all we have to do is look at what? Or this sum, the difference between two will be less than or equal to what? What's this? So if we're going to sum out to n, right? This one is the one right after it. The next one, right? A sub n plus 1, right? Is the next term in the series, right? So the amount that this sum, this partial sum, the amount that it differs from the true sum, the amount of error that we have by stopping is less than or equal to that number right there, the next one out. Okay? So let me give you an example of this. This is really weird having the light coming from the bottom. I feel like I'm like a, yeah, my shadow is very evident to me today. Okay, so as an example, if we take a look at, sum n equals 0 to infinity of negative 1 to the n over n factorial. All right, so if we take a look at that, and we want to say, you know, estimate this. God, all of these are dead. Estimate this sum correct to 3 decimal places. All right, so first what we have to do is make sure that it's an alternating series that converges. All right, so this is an alternating series, right? We could run the alternating series test on this. I'm not going to go through the work, all right? You'd show it's a decreasing sequence. You'd take the limit as n went to 0, n went to infinity, you get 0. It would check. So it's a convergent alternating series, all right? Since it is, and I want to estimate it correct to 3 decimal places, what I want is to figure out where I need to stop so that when you add those up, the answer you get is going to be off from the true answer by no more than what? 3 decimal places means, if you look at a decimal, right? 1, 2, 3. I don't want the first 3 decimals to change in my answer. The last one can change, so I'll put 0.1. This is like 1/10,000th. Does that make sense? I want this sum, when you take its difference between the true sum, right, and the estimate, that I don't want it to be, or I want it to be less than this, the difference. Does that make sense? You sure? Okay. So according to the formula, according to the thing I just put on the board, the difference between the true sum and the nth partial sum has always got to be less than or equal to a sub n plus 1, all right? So, and I want that, right? I want that to be less than 0.0001. So in other words, I want the error to be smaller than this. That way I know that if I keep adding after that, it's not going to change that 3rd decimal at all. You'll see this when I show you. I have a little animation to show that, to illustrate this. Okay, so when you look at this, all you have to do is figure out what this is. Okay, so what's this? The a sub n, remember this, when you look at an alternating series, the a sub n part is only the positive part of this, only the part that's not alternating. So that's the 1 over n factorial, right? So what is a sub n plus 1? 1 over n plus 1 factorial. We want to make sure that that is less than 0.0001. And then what we can do is we can just mess around with this. This is just an inequality. 1 over n plus 1 factorial must be less than 1/10,000th. And then like cross multiply. So you need like 10,000 to be less than n plus 1 factorial. So what n do I need to plug in here to make it bigger than 10,000? And you can check for yourself. 7 factorial is 5,040. 8 factorial is 40,320. So 8 factorial would satisfy this. Okay, so if 8 factorial will work here, then what's n? 7. Does that make sense? So I'll just put here that 10,000 is less than 8 factorial, which is equal to 4,320. Okay, so that means, since this was n plus 1, that means n must be 7.
Just out of curiosity, is that supposed to be less than or equal to the whole way?
This one is less than. This, in the theorem, it's less than or equal, but we want the error to be less than 3 decimal places, or 1/10,000. So that means that if you want to find this sum, if you want to add this up, we know it converges, right? Converges to some number. That number, I still don't know what it converges to. I just know it converges. What I can tell you is that if I stop at n equals 7, that the difference between the true sum and that estimated sum is less than 1/10,000th. Okay, so here's me trying to show you this. Is it this one? Yeah, it needs to be a little smaller though. Okay, yeah. Okay, let me erase this stuff here. By the way, this series, do y'all know what that series looked like? Let's write out the first few terms. We'll do it on the side here. This was sum n equals 0 to infinity of negative 1 to the n over n factorial. So if you plug in 0, what do you get? What's 0 factorial? 1, okay? So, and then 0 up here will give you a positive. So you're going to get 1, then we're going to have minus. Now plug in what? 1? So what do you get? Minus 1, right? And then next one will be plus. Now you're plugging in 2, right? So 2, you get 1 over 2 factorial, right? Then minus 1 over 3 factorial, which is 6, okay? So we start adding these things up. What this shows you right now, do I have this? Oh, I have it starting at 1, darn it. Okay, it's all right. Let's start at 1 so it matches this. All of the results are still the same, okay? If we start at 1 here, then we're going to go like that instead. Okay, so this right here is at the computer doing the sum. So take a look at this. If I do the first, that's just the first one. Here's the first one and the second one together. Here's the third one and the fourth one and the fifth one. Okay, so notice the decimals here, right? 0.633. 6.631. It changed, right? That third decimal changed. Okay, which one am I on? 6? I should be able to get to 7. Let's see, 632, right? Now, from here on out, these first 3 should not change. So if I go to the next one, see that? Stayed the same. Keep going. So these back here are changing, but I'm accurate within the first 3 decimals. And you could do this for any amount of error you wanted. So if you wanted it to be the first 10 decimals, then you would have a different inequality, right? And then you go solve for n. Make sense? Okay. All right, let's move on. So I just thought we would take a little bit of time just to do a real quick overview of series and power series, just kind of to make sure in your minds you understand the differences. So when we first started talking about series, remember this chapter, chapter 8, section 1 was called sequences, right? Okay, now in 8.2 we started with a series. So a series is just a sum of a sequence. That's all it is, all right? And we are really more interested in infinite series, right? So that's all I'm going to refer to here. Here I'm starting at n equals 0, even though when we first started it was n equals 1, equal 1, right? So n equals 0 to infinity here is just adding up what? Just a bunch of numbers, right? We're just adding up a bunch of numbers. We learned that it can either converge, actually go and have a sum, or it could diverge. We can only find the sum of certain series, geometric and telescopic. We have several tests for determining convergence or divergence. That line right there encapsulates that entire sheet, right? That one line. Yeah, we have some tests. This is how we determine if a series converges or diverges. Yes? Okay, so there's a lot of work in that line right there, or a lot of things we need to know. Now, what's the difference between a series and a power series? Well, a power series is a series, but it also includes an additional variable x in it. Okay, so we look at the general form. Here it is, sum n equals 0 to infinity. This c sub n is like the a sub n was from the previous part, right? This is just a number that keeps changing over as we start summing, as we change the n's. This is a number that changes. This right here is just x minus some number to a power. So you start to get this little linear expression in x, right, to start to increase its powers as you move through the power series. This is called a power series about A or centered at A. So this number right here is where it's centered. If you take the A out and you make the A a 0, then you get this power series, right? Same thing, just make A 0. And so this is a power series about 0. And actually, we started with this, and then we generalized it, okay? All right, so what we started to lead into last class was how we can look at a power series as a function. So the convergence or divergence of a power series depends purely on the value of x. The x that you plug in will determine the convergence or divergence. If x is a value for which the power series converges, then we can actually define a function, f of x, to be the power series. And if we do that, then this function is well defined. That means if we plug in a value of x, it will converge, and it will converge to some number, and that number represents the sum of the series. So once you replace x with a fixed number, you're back to the previous topic, which is just power series. Do you all understand that? That's kind of like the big thing here. If I plug a number in here for x, then everything in here is basically one of these now. All right? You no longer have the variable in there because x has been assigned a value. And so once it's assigned a value, then you can determine the convergence or divergence. So if we define a function this way, the domain of that function will be the set of all values of x for which it's defined. In other words, all the x's that make it converge. Now this is where we started. We started this, we didn't really get into it. This is what we're going to get into today. And we are going to lead ourselves to this next thing. This is actually like the main result. And I'll put this back up here in a minute. But this is what basically happens. All right? This theorem says if you're given any power series, all right? Someone gives you a power series. There it is. There's only 3 possibilities when we talk about its convergence. It's either only going to converge at a single point. That means if I replace that x with a. Do y'all see that if I replace the x with a, this is going to converge? Why would it? If x is a, why is that going to converge? Because if x is equal to a, this is 0. And if 0 raised to any power is 0. And so this is just adding up 0 infinitely many times, which gives you 0. That's a finite sum, right? I mean, not finite. It sums to be a finite number. Now, is it boring? Yes, it's extremely boring. But it converges, yes? So it's either going to converge only at a point, or it's going to converge everywhere on the entire number line. That means any x you ever plug in, this thing converges. So it's like the domain is all real numbers. That's the second possibility. Or the last possibility is that it's going to converge on some single interval. And that's it. Those are the only possibilities when it comes to power series. Convergence at a point, convergence everywhere, or convergence at on a single interval. All right? And that's what we're going to get into as we move through. And then I have one last thing. I'd shown you this last class. It was kind of like the motivation for everything. Come on, where are you? This cosine function. Remember I tried to motivate the whole idea of power series, saying, hey, look, we have cosine of x, but maybe we could approximate it with a polynomial. And I tried to use this 1 minus x squared over 2. Do you all remember that? I hope you do. I remember it. Okay, so that right now, this is me trying to estimate the cosine function right now with just this function right here, which is just 1, which is a flat line. But we said 1 minus x squared over 2 was better. So here it is. You can see the parabola right here. And you see how well it matches this cosine curve right here near 0, right? But I said as you walk away, as you move away from 0, you start to lose the accuracy, right? And how did I say I could fix that? Add more pieces to this, right? And I showed you a way we could do it was by trying to match up the function's value, the derivative's value, the second derivative's value, third derivative's value, right? And so here's me trying to match up. Here's the next one. So you can kind of see it here. I left the previous one, I left here, right? Here's the parabola. Here's the first one, second one. Do you see the black one here and the red one? See how better that is than this one? And I could get even better by going further. And check this out. This is the part that I think is mind-blowing here. Let me zoom out. Okay, so I'm going to zoom out on the cosine function. I need a little more range on that. Hold on. Okay. All right. Let me back it up. Okay, there's the line. Not a good approximation. Parabola, better, right? That fourth degree polynomial, even better, right? Now watch. Just watch what happens to this curve as I march through and make this series become bigger. See it go down now? Here? And now I'm going to go a little faster and just watch this thing. It's freaking amazing. Watch my polynomial start to fit itself. Do you see it? It just like basically fit itself right on top of that cosine function. Right? Now maybe I need to zoom out because x max. Because you're kind of maybe thinking, oops. So look how good it is. Like in here, look how freaking good this is. Now, it starts to fall apart right here, right? This polynomial, I'm out to a 16th degree polynomial, but it's kind of not very good out here, right? So what do? More, right? I just keep going, and I'm going to start marching this thing. See it? Now it's good over here, right? And when does this thing stop? Never, right? And so if you march it forever, it basically covers up cosine, and it becomes cosine. That makes sense? And why do we want this? Why would we rather deal with this than cosine?
Real numbers.
I mean, we have cosine, so why do this complicated infinite polynomial? Okay, but why do a series? Like, what's the advantage of having a series?
Like in real life, or like I guess if you were building a building and you needed to have 20-something decimal places worth of precision to like link up two walls on the outside of the skyscraper.
But can't we just use the cosine function for that? Like just go to a computer and type in cosine?
You need to give it parameters for that.
Well, how's your computer doing cosine x? With the power series, right? I mean, so what do you do when you don't have power series? You don't have computers. That's what you do. You don't have computers. Does that make sense? Like we take it for granted that when you type in cosine of, whatever, and our calculator just spits out a decimal, we just take it for granted that before the calculator, that wasn't happening, all right? That wasn't happening. Also, I'm restating this because I stated this last class. The importance of power series is that they're easier to work with. You can differentiate a power series easily, you can integrate a power series easily, and that means there are no limitations to what we can and cannot differentiate and integrate. Right now, if I put an integral on the board, just randomly, right? I'll just throw one up here. There.
I had it at x.
Integrate that. Oh, sorry, dx. Okay.
I had it at x to the third. No.
Yeah, I had you here, right? I mean, if I put this in here and said, let's integrate this, you're not doing it, right? You're just not doing it. Now, is there a power series? Is there a power series for e to the x squared? Yes. Sine of that? Yes. Can I get a power series for that? Yes. Can I get a power series for this? Yes. I can turn these all into power series and then do whatever arithmetic I need to do, come up with a new power series, and then just integrate the power series. And we're going to do that, okay? We're leading to this where I'm going to give you some function, and I'm going to tell you convert it to its power series. And I'll do it, and I'll put an integral here, a definite integral like 0 to 1 or something, and then you go and you actually evaluate the integral, all right? Okay. So, do you remember I said a second ago there's 3 possibilities, right? So, sir, I'm going to give you and you an opportunity to give me one of the 3 possibilities when we talk about intervals of, or convergence of a power series. There's 3 possibilities.
On the line, on a set interval, and on the 1 point.
Okay, so number line, like you mean all the numbers, right? All the numbers. Or a single point
Or on a specific.
on an interval, right? Okay, so for this power series, what do you think the convergence is? Do you think it's at a single point? Do you think it's at an interval only? Or do you think it's everywhere? So as I kept on marching through and adding more and more, was this thing covering up the function? Or was it only working in one little area or only at a single point? It looked like it was working everywhere, right? As I kept going and growing this, it kept on doing that thing. So we're going to see later on that the power series for cosine, the convergence is everywhere. So you remember how I said you have to stay close to 0? That's only if you're going to do the first 2. Like if you're only going to do those 2, you better stay near 0. But if you want to use the whole series, then you can go anywhere you want on the function and that thing's going to work. Does that make sense? I'll say that one more time. Right now, if I just use these first 2 and I say, what's cosine of 4? I'm going to be way off because I'm too far away. But if I use a bunch of these and say, what's cosine of 4? Then that's fine because I can go anywhere I want on the number line as long as I use enough of these. Okay, let's get into some examples. All right, so what we're going to do now is I'm going to put a power series up here and we're going to determine for what values of x it converges or diverges. I did one of these last class. Where is it? Did I do the 2x minus 5 to the n over n? I did, right? Okay. Did I go all the way with it? Okay. Let's just start that one over. So we have this sum n equals 1 to infinity of 2x minus 5 to the n over n. Okay, the question here is for what value of x does this converge? So I'm one of the lead instructors for Cal 2, and we were having conversations with some of the other faculty, We were talking about, we have to, on every final exam, we have to put a problem in, that the whole department puts this one problem on the test. And the one we've been using is an integral. And we're going to change it over to a problem like this. So my point is, something like this to me is like, you should see this, number one, you should see this in Cal 2, and then number two, there's a lot going on in this problem, all right? So the way it's going to be formulated, in a few minutes I'm going to formulate this question in a slightly different manner, but the actual mechanical thing that we're going to do is the same, all right? So we want to know the values for which this converges. So we want to use a ratio test here, right? That seems to be the nice test that we learned last time. So if we run a ratio, what does the ratio test say? I need to take the limit as n goes to infinity, the absolute value of a sub n plus 1 over a sub n, right? Like that? That's what I need to do. Okay, so if I do that and I take the limit as n goes to infinity, and let's see here, I'm going to have 2x minus 5. We did do some of this, yes or no? I feel like we did. To the n plus 1 over n plus 1 over 2x minus 5 to the n over n. I'm supposed to figure out the limit of that. I'm going to flip things over and also going to rewrite this piece right here as 2x minus 5 to the n times 2x minus 5 over n plus 1, and then times n over 2x minus 5 to the n. Okay, so that's just this flipped, and then this rewritten, and then broke up that numerator. We did all this, I think, last class. I think we went through all the algebra here. We get some things to cancel. This cancels, right? And so what we're left with is the limit as n goes to infinity of the absolute value of, so I have 2x minus 5 on top and I have n, right? And on the bottom I have n plus 1. So what you should get in the habit of doing is putting your n's together and separating the thing that has the x in it from it, like that. Okay, so I put n over n plus 1. And now, we're ready to take a limit. What is this limit? As n goes to infinity, infinity over infinity, L'Hopital one time on that, you're going to get 1 here, right? So the limit, that's 1. N is not here, right? So n has no impact on this, right? So here's where we are. When we take that limit, we get the absolute value of 2x minus 5. That's what we get, right? So the ratio test says if we take the ratio of a sub n plus 1 over a sub n, take the absolute value, this is what we get. The ratio test will only give you convergence when what? When that is less than 1, right? So we're trying to figure out when does this thing converge. That means we need the ratio test to give us an answer that's less than 1. So my question now is, when is that less than 1? Whenever that's less than 1 is when I'm going to have convergence, right? Agreed? Okay. Now, a real quick little side note about inequalities. I mean, not inequalities, absolute values. This is going to be helpful as we move on. If I say the absolute value of x is equal to 4, then what's x equal to? What can x be equal to? 4 or negative 4, right? Then here x could be 4 or negative 4. Okay, that's an absolute value equation. What if I have this? Absolute value of x is less than 4. That's an inequality, right? So this means, what does this mean?
Can't be 4.
Can't be 4, but it could be 3, it could be 2, it could be 1, it could be 0, it could be negative 1, negative 2, negative 3, right? So, would you agree with this? Would you agree with that? your x value must be between -4 and 4. So like on a number line, here's 4, here's -4. We're saying all the values in between here, not including the two endpoints. Everything between -4 and 4, right? So the moral of the story is this. If you ever want to turn an absolute value inequality into something easier to work with, what you do is you drop the absolute value, okay? See that? Drop the absolute value. And then on the other side of the x, you put greater than, and you put this expression negative. Let me do one more. What if we wanted to know when the absolute value of x minus 1 was less than 2? So how would we do this? First, we drop the absolute value and write the inequality. Okay? Then, on the other side, we put greater than what? -2. And now, to figure out what x is, we want to get the -1 out of here. We add 1, add 1, add 1. And so what does that tell us? X is between -1 and 3. Okay, that's how we go about solving absolute value inequalities. Linear ones. If they're quadratic or something, it's more complicated, but for linear ones. So if I want to know what my restriction on x is, what I'm going to need to do is that step right there. So first thing is I'm going to drop the absolute value. And then what am I going to put on the other side? -1, less than that. And then let's solve now for x. Okay, so add 5 everywhere. When we add 5, what do we get? 4 less than 2x less than 6, right? That's adding 5 here, adding 5 here, adding 5 here. And last step, divide by 2. So 2 less than x less than 3. Okay? So, as of right now, please pay close attention. I realize it's like the week of Thanksgiving. Everyone's shutting down. A lot of y'all look tired. Okay? But like the next couple of days is going to make the difference between passing or not passing that final exam. I mean, it's really going to, you have to understand this, all right? Okay, so we have determined that we will have convergence, right? If x is between 2 and 3. So if you right now hand me a number between 2 and 3, and I plug it in here, like let's say 4. If I plug 4 in here, I promise you it converges. All right? Okay? Give me 4, plug it in, I'm going to get convergence.
You said it has to be between 2 and 3 though?
Did I say 4?
Yes.
Okay, so you are paying attention. Thank you. 2 to 3. So if I pick 4, it's not going to converge. It's going to diverge. If I pick 2.5, right? It's going to converge. Sorry about that.
Good play.
Yeah. What's that?
25 abs, just because it would have made that top part 0.
When you were just initially?
Yeah.
Yeah. So if we pick a number between 2 and 3, right? Anything though, it could be 2.1, it could be 2.999. We're going to get convergence. But here's the one thing we still have to think about. The reason we got this interval is because the ratio test told us that as long as this thing's less than 1, right, we've got convergence. What if this thing's bigger than 1? What if this thing is bigger than 1? What do we have? Divergence. But what if it's equal to 1? Inconclusive. Okay? Inconclusive. So right now, what we've done is we've said, look, I'm trying to figure out what x's make that converge. I know by the ratio test that as long as this is less than 1, I'm good. Like, this is what I need for convergence. But if this is equal to 1, the test fails. Right? So what would make this thing equal to 1? That would be if we did include these two endpoints. Do y'all see that? So what we know is this. We have convergence. We have convergence in here. Okay? Check. We have convergence in there. We know that outside of that, we fail. We have divergence. Divergence here. Okay? Fails. What we still don't know about is what's happening here and here. So at 2, what happens? At 3, what happens? Do y'all see that? Okay, so now what we have to do is we actually have to check each of the 2 endpoints. Okay, so I'm going to go back to the beginning of the problem, way here, right here, and I'm going to say, all right, let x be 2. Let x be 2. Yes?
I thought we didn't know where, like at 1, we didn't know what happened. Or no?
At 1, we didn't know what happened?
It's inconclusive, so we don't know.
No. When the ratio test gives us 1, right? So the ratio test gave us this, right? That's what the ratio test gave us. When this is less than 1, we have convergence, which is what gave us this interval. But now we're asking ourselves what would make that equal to 1, because then the test fails, right? But there's only 2 places where the test fails. It fails at 2 and at 3. Those are the only 2 places where the ratio test, I have to throw it out the window. But since it's only 2 places, let me just check those 2 places. And I'm going to check it manually by going back to the original series. So let's go back here, okay? Does that kind of help? Let's replace x with 2, all right, and rewrite the series. Sum n equals 1 to infinity. And now we have, what does that become if I replace that with 2?
Alternating.
4, so 4 minus 5, that's negative 1 to the n over n. Okay, this is no longer a power series. Do y'all see that? This is a series, 8.2, 8.3, 8.4. So you look at it, you say, what kind of series is that? It's an alternating series. How do I check to see for convergence on that? Alternating series test, right? It's an alternating series. Now, why would we not use the ratio test? Because we already know if I did the ratio test on that, what would I get? I would get 1. Like, I know that. That's how I came up with that. So I'm just going to do a quick alternating series test. Okay. What is the a sub n for us here? What's the positive part of that thing? 1 over n. Okay, so what are the things we have to check for the alternating series test? The limit goes to 0, so let me check. I'll check. It doesn't matter what order we do this in. Limit as n goes to infinity, 1 over n, that's 0, check. Okay, what's the second thing I have to show?
A sub n is bigger than a sub n plus 1.
Yeah, so a sub n is bigger than a sub n plus 1, right? Eventually, that it's descending. So is that true? Is 1 over n
Yes.
bigger than 1 over n plus 1? Check. Okay? So what is it? What do we have? This series what? Converges, which means that, remember how back here I was saying I'm not quite sure what happens at 2? Now I know what happens at 2. It converges, which means I want to include 2 in my answer. Right? See, for what values of x. So this inequality now becomes that instead, right? Agree? Now, what else do I need to check? At 3. Okay? So if we do x is 3, now you do 2 times 3 is 6, take away 5, that's just 1. And 1 to any power is 1. So the top is just 1. And what type of series is that? Harmonic. And what do harmonic series do? Diverge. Harmonic divergence. Which, yes?
Can you ask for the radius too, like on it says?
Radius? What radius?
You put like R, and then,
I haven't talked about that yet. Yeah, I'm going to, but I haven't like said what R is yet. Okay. So that means now that, do we want to include 3 or not? We do not, right? We do not, because that would be divergent. So at the end of the day, final answer, for what values of x does this converge? You would basically just say x. You could say this, or you could say, it must be an element of the interval 2, 3. Bracket on the 2 means we include it, right? Parenthesis on the 3 means we don't include the 3. Now remember, I put that note up and I said there's 3 possibilities, right? And I haven't really formally gotten into this, but there are 3 possibilities when it comes to the convergence of a power series. It's either at a point, at everywhere, or it's going to be on an interval. And this particular power series converges on an interval. Do y'all see that? Only on an interval. Okay, let's do another one. See, let me explain why I like these problems. I think it's kind of self-explanatory, but you first have to, a problem like this appears on some Cal 2 test. The student had to have gotten through sequences and series, right? They had to have made it to this section, which some teachers don't make it that far. And then once you do a problem like this, you're going to wind up having to always check the two endpoints. Well, not always, sometimes. And for each of those checks on the endpoints, it could be two different tests you're running, right? Alternating series test, that one was harmonic, but what if one of them was one thing and the other was something else? I mean, it's like 5 problems in one here, kind of, yes? Yes.
So if 3 ended up being divergent, is it also fair to say?
3 is it's divergent at 3.
Yes, I'm sorry. I mean, in addition to that, if we were to try anything further than 3, 4, 5, 6, 7,
Yes.
9, all of them would then be divergent
Yes.
based on that initial assumption.
That's right. We know that it can only be between 2 and 3, and then we found out that at 2 it does converge, and at 3 it diverged. So now our interval looks like this. It's this endpoint's included, that endpoint's not. It only converges in here. Anything outside of that interval, it diverges. So if we were to actually want to talk about this as a function, right, a function, then the domain of this function is that interval. So this function is only defined on that interval, and that's it. It'd be a weird function to only be defined on an interval, but a small interval, but it's okay. We have workarounds for that. We have ways to make things work for us. All right, so let's do the same thing for what values of x. Oh, you know what? No, that's not. This is the way the problem is stated. Sorry. Example. An order 0 Bessel function is defined by capital J subscript 0 of x equals sum n equals 0 to infinity of -1 to the n x to the 2n over 2 to the 2n times n factorial squared. That is what we call an order 0 Bessel function. There's an order 1 Bessel function. This function, so instead of using f of x, we're using capital J sub 0 of x. That just lets you know it's a Bessel function of order 0. And this is what it is. These functions are actually used in like harmonics. They're used to model things like if you have like a drum and you have the membrane on the drum that's vibrating, right? This function can be used to help model that, all right? That's not that important. What's important for us is we would like to know, okay, we would like to find the domain. So what is the domain of this function? Well, that means what are the values of x that I can plug in that make it converge, right? Which is the same question we just had. All right, so how are we going to go about this? Yes?
Do like the ratio?
Yeah, ratio test. Let's start with the ratio test. I told you it was the almighty ratio test, right? Because it is almighty. Limit n goes to infinity. Okay, here we go. I've got to plug in n plus 1 into this first, right? All right, so it's going to be -1 to the n plus 1. X to the, be real careful here, x to the what? 2n plus 2. Because if you replace that with n plus 1, the 2 distributes through, right? So you get 2n plus 2. And then here, same thing, be careful. You're going to go 2 to the 2, what is it? 2 to the 2n plus 2. And then here, be careful here also, this is n plus 1 factorial squared. Isn't that what that is? That's just me replacing all of the n's with n plus 1s here. Now I'm supposed to divide that by this, right? Divide by this, but I told you I'm going to skip that step and just go ahead and multiply by the reciprocal. So I'm going to say times 2 to the 2n n factorial squared over negative 1 to the n x to the 2n. So I'm going to take a look at that limit. I'm going to see where it goes, right? See if I can't cancel anything. What should I start messing with here?
Separate the n's and ones, so you'd have n or one.
Like this one right here?
That one, yeah.
Now, these I'm just going to say bye-bye to, right? Because it's absolute value.
Yes, so it's x to the 2n times x to x.
X to the 2n times x squared, right? That's what that is up here, this right here. And then this one right here is what? 2 to the 2n times 2. So I'm not looking at those anymore. 2 squared, sorry. 2 to the 2 squared. Anything else I can do? Yes?
Simplify the factorial.
This factorial, right? I have an n factorial here. I have an n plus 1 factorial. We learned that you can rewrite n plus 1 factorial to be equal to n plus 1 times n factorial, right? I'm going to use that right now. I'm going to rewrite this as n plus 1 times n factorial, but that's squared, right? This right here is that, but then it's still squared. And then I'm going to go one step further. I'm going to say that's n plus 1 squared times n factorial squared. So I'm going to go from here to here. Does that all make sense? Because this is multiplication right here between those two. You can do the squared on each of the factors. Yeah. Yes?
So minus 1 and to the power plus 1.
These are gone not because they cancel, but because at the end of the day we're taking an absolute value. And so the absolute value of negative 1 is always going to turn out to be 1. So I'm not technically canceling these from each other, just ignoring them. All right, we should get lots of nice cancellation here, shouldn't we? Let's see. That's gone. This is gone. This and that's gone, right? All of that. Yeah? Okay. Let's see where we are. I'll erase this. So we are at the limit as n goes to infinity. Absolute value. Let's see, what's on top?
X squared.
X squared, that's it? Okay, so I'm going to separate that. I'm going to put it over here as x squared. All right, now what about the other stuff that doesn't have x's in it?
4 times n plus 1.
4 times n plus 1 squared, right? That's it. And then a 1 on top. So make sure you write that as a fraction. 1 over 4 times n plus 1 squared. And now you let n go to infinity. Are there any questions on that? Sure? Where anything went, or where anything canceled out or anything? Sure? Okay, let n go to infinity. What happens? This thing goes where? 0, right? And 0 times x is going to be 0, which means that this thing goes to, after the limit, 0, right? And our question was, when is that less than 1? And when is that less than 1? Always. Which means the domain of this function is everything. See, no matter what x you ever fix, if you give me an x right now and tell me to fix it, right? 10, let's say. 10 squared is 100. When you do this limit, this is going to zero that out. Okay? No matter what. So because this is always true, this is true for all x, the domain is all real numbers. Excuse me, sorry about that. Negative infinity to infinity. If you want to look at it like an interval, you can, but it's everything. Okay. Any questions?
Yes.
Yes.
How is it positive infinity? If it has to be less than 1.
No. This is the result of the ratio test. When we do the ratio test, we get that the ratio test spits out 0. Which we always, when we run the ratio test, we always ask ourselves, when does that ratio test give us something less than 1? Always, right? Always. So regardless of what x I plug in, this thing's always going to be less than 1, so that means I can plug any x in, which means the domain of the function is everything. So if you go back now and look at your notes from today and last class, I have now given you an example of each of the 3 types. Last class, we did a problem with the ratio test where when we had this limit right here, this piece right here was going to infinity. And I said the only way to control that is to make x 0. Right? You have to look back at your notes. And that's the example of a single point. The example before this, we got an interval, right? And then this example, we got everything. So you now have seen an example of each of the 3 possible scenarios. All right, so let me go back to this overview. Okay, so let's see if this kind of makes a little more sense now. Given any power series, it converges only at a single point on the entire number line. That's the one we just did. Or it converges on an interval, which was the problem we did before. Now, when we talk about convergence on an interval, a single interval, a couple of things about that. First of all, if it converges on an interval, there exists this capital R such that if the absolute value of x minus a is less than r, it converges. So for us, go back and look at your work for the problem we did. We got to a point where it said absolute value of 2x minus 5 was less than 1. Do you remember when we got to that? Okay, this is the answer that gave us an interval, right? Okay. We had to check the endpoints, didn't we? But if we can make it look like this, then we will identify this thing called R. And this thing called R, or this thing R, is called the radius of convergence. So can we make this look like this? So all I need is a 1 in front of the x. So I'm going to pull a 2 out. So if I pull a 2 out, I can pull it out of the absolute value. But I have to pull a 2 out of this also. So I get that, right? Must be less than 1. And now what? Divide by 2. Does that look like this? Okay, then what is R? R is 1/2. Okay? This is R. And that is called your radius of convergence. Now let's try and make sense out of that number now. Okay, because that's just a number like 1/2, right? So do you remember what our answer was for that? What was the interval we had? 2 to 3, include 2, right? Don't include 3. Okay, what's the number right in the middle of those two? It was 5/2, right? That's the number right in the middle. That's not important. Okay, that's not that important in terms of, we never use that as part of our answer. But radius, when you think radius, you think distance from center, right? If our radius of convergence is 1/2, then if you go from that center point this way by 1/2, where would you be? At this end, right? And then that way. So this is like, it's almost like a little circle. It's not a circle because it's just a number line, but the radius is that distance